Welcome, friends. So I thought I'd do, by way of wrapping up our unit on AC motors, I'd do kind of an extended review of these quizzes. These, of course, don't cover everything that we covered about AC motors, but it gets a lot of the fundamentals. And of course, there's the video lectures, the other ones. They're on YouTube if you need a refresher on some of the other things. Okay, so this is the morning quiz. I might do the second one in a separate video. It's a little bit of a judgment call. It's very similar material, but different questions. So we'll see how that works out. So we're given our usual set of potentially useful equations. We're considering a synchronous AC motor that has a permanent magnet on its rotor and two electromagnets on the stator, like the toy one that we discussed in lecture. Okay, we saw that picture quite a few times. It looks something like this. So we got our north, our south, and then we've got electromagnet and electromagnet, and those are connected to each other and to an AC source, something like that. Okay, so part A, would the rotor still continuously rotate if the AC source was replaced with a DC source? Why or why not? Okay, so as the name AC motor suggests, DC input shouldn't work, and indeed it does not. And the reason, though, is that if you have if DC, then constant voltage and constant current. Okay, so if that's the case, then let me change colors here. If this was DC, so if we imagine that instead of AC we had DC, so in red there, a little battery, then we would have just a fixed magnetic field. So say if that was the north and the other one was the south, we'd have a bunch of magnetic field lines that way. And the rotor would rotate from its current position until it was sort of aligned with the magnetic field, right? Like a compass needle. And once it got to that point, it wouldn't rotate any further because it's aligned with the magnetic field, so it would no longer feel a torque. And because the magnetic field isn't changing, because the voltage and the current through these electromagnets wouldn't be changing with DC input, then it just wouldn't rotate anymore, and we wouldn't really have a motor, would we? So if DC, then constant V and constant I, which means constant magnetic field, B. And that, as I explained, would mean zero torque after it aligns. Okay, so you didn't have to give all of that, okay, but something along those lines is what I was looking for with the why or why not in that question. All right, so B, briefly explain why the movement of the rotor in this type of motor is referred to as synchronous. In other words, explain what the rotor is in sync with. Okay, so it is in sync with the rotation of the magnetic field produced by the stator. Okay. So remember that the way that we explained it, just to get the idea, is that you have first a north pole on this electromagnet and a south pole on this one, and then half a cycle later you have a south pole on the left-hand electromagnet and a north pole on the right. And so effectively you've rotated the magnetic field by 180 degrees during that process. And if this is a synchronous motor, and if you have a synchronous motor, and we do here, then the rotation of the permanent magnet is going to exactly follow that rotation of the magnetic field set up by the stator, right? Because it's going to feel a force so that it is constantly trying to align with that changing magnetic field. Okay, so question 2, say that we were told induction motor connected to an AC source, has been for a long time. So in other words, we didn't just connect it, it's been connected and it's doing its thing. And the torque on the rotor is very small. Okay, so that's the crucial thing. Okay, torque is very small. You may assume that this is a normally functioning motor, nothing's broken, etc., etc. Okay, so what can you deduce about the current flowing through the squirrel cage bars? All right, so if the torque on the rotor is very small, that suggests that the rotor speed is pretty close to the synchronous speed. In other words, the speed of rotation of the magnetic field, right? So we had this, there's an equation up here at the top that tells us what the synchronous speed would be. So V sync is 128, blah, blah, blah. We're not asked for that number here, okay? But we know that with an induction motor that the rotor speed is less than the synchronous speed. I'll just call that V sync, like in the equation at the top of the page. All right, but it's only a little bit less in this case. And the reason we know that, okay, is that slip, as I talked about in the lecture video, okay, so the slip is equal to difference in rotor speed and V-sync. Okay. And the more slip you have, the larger the difference is between these rotor speeds. So in other words, the larger the, or more rapid the change in magnetic field is through all of the little loops around the squirrel cage rotor, okay? Because you can go to an extreme example. If the squirrel cage rotor was 0 speed, so if rotor speed was 0, then slip would be huge, right? It'd be, rotor speed would be 0, and V-sync would be whatever it is for, you know, the given frequency and the number of poles and the number of phases being fed in. And so you'd have this huge slip, which means that from Faraday's law, right, good old Faraday's law, okay, this rate change in magnetic flux, this rate change in the number of magnetic field lines through the loops of conductor, well, that's going to be big. And so you'd induce lots of voltage there, and so you drive a lot of current through the squirrel cage bars, okay? That's why they're so fat. They're made out of big chunks of aluminum typically, unless you're talking about a pretty little induction motor. So, because they need to be able to carry all that current when they're just starting up and the slip is really big, right? When their rotor speed is really low. Okay, but now that we've gotten to this point where the torque on the rotor is very small, well, that implies, so, we're running out of space here, but torque, low torque, implies low current, right? Because we can think back to the Lorentz force in the DC motors section that we just finished up. And we know from that that if we don't have much torque, we don't have much force. And if we don't have much force, then we aren't going to have much, well, if we don't have much current, we're not going to have much force, right? So if we know that there's not much force, then we know that we have to have low current. Okay, so low current is answering this question, right? Deduce about the current flowing through the squirrel cage. So low torque equals low current, and the reason for that is the stuff that we just talked about, all right? Because if we have a small slip, so the difference between rotor speed and V-sync is small, well, then the rate change in number of magnetic field lines isn't very big because the rotor is almost exactly following the synchronous speed, and so the number of magnetic field lines through all of those loops on the squirrel cage doesn't change very quickly, and so the induced voltage there is small. That means that the that means that the current that flows in response to that small voltage is also relatively low, and that would result in low torque, okay, which is the condition we're given. All right. What can you deduce about the rotor velocity of this motor? Briefly explain. Okay, so we've kind of already gone through that. If you have a low rotor velocity, then slip is big. If slip is big, then the rate change a number of magnetic field lines. And if you're not clear on that connection, go back to that video. I think it's called The Need for Slip, one of the last ones that I did, and check that out. But if slip is big, then this is big, and so induced voltage is big, and we have big current and big torque. In this situation, though, we know that we have low torque, or very small torque, and so we know that we have low current, which means we have low induced voltage, which means this, the rate change of those number of field lines, okay, through those loops, must also be low. And if that's low, then the slip must be relatively small. So a small difference in rotor speed versus synchronous speed. And so the rotor velocity here is probably about as high as it's ever going to get. So at max or near it. And the explanation is what I just talked through, and it relates to what we already talked about and wrote out up here. All right, next page. Last question. So consider this AC motor receives 3 phases of AC electricity. So we've got one phase going into that pair, second phase going into that pair, third phase going into that pair. And the frequency of the AC electricity is 60 hertz. So that's key and that's key. A, what is the speed of the rotor in this motor under normal operating conditions? All right, so a couple of things. First, we need to recognize we got a permanent magnet on the rotor. We don't see any squirrel cage, so we're talking about synchronous motor. So in other words, the speed of the rotor is going to exactly equal the speed of the rotation of the magnetic field, V sync. So V sync, we go to that equation, is equal to 120 times the frequency divided by poles per phase. Okay. If we write that out, this calculation here, we got 120, we've got 60, we've got a number of poles. So here all we need to do is count them up. If you go searching on the internet, though, be careful, because poles as a definition is sometimes in engineering circles talked about in terms of not like individual windings. It's talked about this ratio, number of windings per phase, okay? Because we've talked about poles, like magnetic poles, and we have associated them with individual electromagnets in this class, I write out the equation this way so that when we are counting up poles, all you need to do is say 1, 2, 3, 4, 5, 6, just like I did in the video. And so there are 6 poles, and there are 3 phases of electricity. So 6 over 3. The numerator is 7,200. The denominator is 6 divided by 3, so 2. And we've got 3,600 RPM. Now, for part B, if a permanent magnet is replaced by a squirrel cage rotor, how would the rotor speed of this new motor compare to part A's result? Okay, so we've already talked about this earlier in the quiz, but we know that in an induction motor, the rotor speed is always less than the synchronous speed. And we know that because you have to have some slip to have any torque on the rotor. So if you're dealing with a squirrel cage, right, which we're doing here, then we're definitely talking about a situation where the rotor speed is less than the synchronous speed, which means that it's less than part A's result, okay? So Thanks for listening. I'll go over quiz 2 in a separate video. Similar concepts, but we might talk about a few other little bits and pieces, so you might want to tune in. See you then.